Hello everyone and welcome to the webinar this afternoon around submersible pumps and motors and their failure warning signs and how to overhaul and test. So we'll just get started. So if I just ask a wee bit of housekeeping at the start. So if you've got any questions you want to ask throughout the webinar, feel free and to add them into the question and answer chat box that we've got, and myself and David, who's presenting alongside me, will do our best to answer the questions. We might ask some questions throughout the webinar if we see any popping in, and we'll also have, hopefully, keep 10 minutes spare at the end where we can ask any questions that we don't get to throughout the presentation. So this webinar will also be recorded and available on the Trillium YouTube channel a few days after this broadcast. So I'll move on to the next slide. So just sort of introducing myself and David. So I am Callum Warnock and I've worked for Weir Engineering Services, Trillium Flow Services UK Limited, my whole career, starting as an apprentice, and I'm currently the operations manager for pumps based out of the Alloa Service Centre. So you can see the image of the Alloa Service Centre down below. So the Alloa Service Centre's got approximately 12,000 square metres of workshop capacity, and it's really the central hub for our submersible motor and pump offering within Trillium, with a bespoke test loop and experience spanning 70 years in the submersible product. So introducing David. So David's the real expert on submersibles. David is the technical manager for wet wound submersibles and performance testing based in the Alloa Service Centre. David has over 15 years experience working on submersible pumps and motors, both from a full service overhaul, new supply and root cause fault finding basis. So David's educated mechanical engineering, but he's also got extensive knowledge of the electrical principles involved in the manufacture, service and testing of submersible pumps and motors. And hopefully between us we'll be able to give you some of that information today. So I'll move on to the next slide. So it's really a background on Trillium. So Trillium designs and manufactures mission critical equipment such as valves and pumps, and provides aftermarket parts and services to the global power generation, industrial, water and wastewater, oil and gas and other aftermarket orientated process industries. So you can see on the slide that I've got on the screen, you can see in the green colour we've got our valve and actuator brands, and then in the darker blue we've got our pump brands, and then we've also got our Allen Steam Turbines brand based out of our Bedford facility for Trillium Flow Services UK Limited. So as I described earlier, we've got our Alloa Service Centre, which is based in Scotland in the United Kingdom. So as you can see, the global reach of Trillium is quite extensive, and we all work together to try and provide a good offering to our clients in the flow control space. So moving on to the next slide. So as you can see, this is effectively the history that Trillium's got. So Trillium Flow Technologies' heritage of innovation spans over 190 years. The corporation is not standing still, adding new products and services to make our customer processes more efficient and productive. So as I described earlier, we manufacture mission critical equipment such as pumps and valves, and also provide aftermarket parts and service to the global power generation industry. So effectively, what we do is provide an extensive network and knowledge base to service not just Trillium products, but equivalent product ranges from third-party providers, all with a confidence and reliability of extensive service range from an original equipment design and manufacturing product platform. So you can see from the slide the experience that we've got in a number of fields and valves and pumps and steam turbines. Now, what's not touched on in this slide is the Weir submersible product. So that's predominantly a big mainstay of the Alloa facility, the overhaul of those units. So we'll touch on them throughout the slides as we go along. So I'll move on to the next slide before we before we move into the technical detail. So this is our Trillium product overview life cycle service model. So I'll just spend a few minutes tying this to what we're going to be discussing today. So as you can see here, our integrated service solutions, total value maintenance support. So in terms of what we offer, in terms of an embedded engineering / a field service solution, alongside the overhaul and testing of the submersible motors, it's absolutely critical not just to get the strip inspect report correct, the overhaul that we're going to be discussing, and then the testing in the facility. It's also crucial that these submersible motors, when they go offshore or wherever they're going in the world, that they get installed correctly, they get set correctly, because that's as big as and much important to how they end up running, and hopefully have got a long lifespan ahead of them. In terms of inspection and monitoring, so we'll touch quite a bit on condition monitor later in the slides, operational performance, and also touch a wee bit on NDT and different NDT techniques that can be done while we're overhauling these units. Product service training, so it's something else that's offered within Trillium around training of clients and customers, not just in the submersible space, but also pumps. If our clients and customers can have some experience and have some intel in the typical failure modes and different things to look out for in rotating equipment failures, they can spot trends, they can start highlighting things, phone into us, and we can start looking at early intervention techniques or bringing forward maintenance, which will hopefully effectively reduce the cost and critical downtime maintenance. David's going to do a slide on upgrade and re-rates and our advanced parts solution offering within Alloa. So that covers the left-hand side. Moving on to the right-hand side, so we've got a good number of slides on what we do with the submersible product range in terms of strip inspect report, overhaul and testing, and the different jigs and fixtures that we've got to support that. Our key field service elements, so I've touched on that already, critical to our offering. And then also our engineering hub, which is a team of engineers, not only within the Alloa Service Centre, but also off-site to that within the Trillium organisation, to look at CFD analysis and root cause analysis that we'll discuss in these slides as well. So I'll stop talking now and I'll move on to, well, I won't actually, I've got another slide to discuss, so the agenda. So I'll quickly run through the agenda before I pass on to David. So what we're going to be discussing today is a bit around submersible motors and the early principles of them. Then I'll go on to discuss the inspection and overhaul process, how we do that. We'll then discuss around the testing of them, the no load and then the load testing, and then some review of operational applications, failure modes, key indicators, upgrades, and then a bit of time for conclusions and recap. And as described, if you've got any question, please ask it throughout the webinar. So I'll now pass over to David and he'll kickstart.
Thanks for the introduction there, Callum. Afternoon to everyone who's joining us today, and thank you for taking some time to listen to us on the submersible motor product. First slide here, I'm going to take you through just a little bit of history on the submersible motor as we see it. So Trillium Flow Technologies, the site here in Alloa, has been involved in the manufacture and repair of this unit for more than 70 years, as Callum had touched on, so quite an extensive array of history on this site itself, with knowledge passed on generation to generation, which gives us a very good advantage when it comes to repairing these type of product. As described here, the unit was originally designed for deep well water recovery and mines drainage. Originally, these were very small units, but quickly developed, and nowadays we can see units up to 11 kV in service around the world. The motors we're going to focus on today are water-filled and water-cooled units. We do see in the marketplace today some oil-filled alternatives, which we do have experience in Alloa of overhauling and repairing, but predominantly the sites today are going to focus on the water-filled version of these units. One of the key differences from a submersible motor to a conventional motor, as we term it, is that a conventional motor is obviously cooled by air, whereas the motor that we're talking about today is pumping its own cooling fluid, which is the water inside it. The submersible motors typically tend to have an integral length of power cable fitted, which is terminated inside of the motor to the windings themselves. Conventional motors, again, would tend to have shorter tails based on where they're going to be situated in operation, whereas some of these submersible motors, as we'll talk through later slides, can be up to 60, 70 or 80 metres deep underneath oil rigs. Next slide, please, Callum. So some of the general applications that we see in the submersible product that we're going to focus on today is the seawater lift, the fire pump and the drains pump. Seawater lift, these are generally the feeding cooling systems and supply to the seawater injection systems offshore. These units typically run consistently, and the discharge pressures can vary depending on demand. The pumps will change depending on the flow rates and customer requirements. Fire pumps, again, designs very similar to the seawater lift applications. The difference with the fire pump duties is the pumps obviously have to go much further out on head and flow as part of the fire pump regulations. These may only be tested monthly when they're in situ, so they're not running continuously. And these should have a dedicated power generation topside for supply in the event of a fire. The drains pump operations, so some hazardous areas do utilise the submersible product for pumping fluids, as it's fully enclosed. Some of these motors do come with ATEX rating, which adds a complication in the repair process and the manufacture process. This can be stuff such as oil tanks. There is other industries that do use them, which is predominantly mining and water industry. We do deal with some water industry submersibles for the service, but predominantly today we're going to talk on the oil and gas product. Next slide, please, Cal.
All right, thanks, David. So what we're going to run through now in the next few slides is the inspection and repair process. So I'll move on to the next slide. So what we've tried to do here is map out our process for strip, inspect and report of the submersible motors. So commonly known as the SIR process. So when the submersible motor comes into us, whether that be coupled with a pump or just the motor alone, first thing we do is carry out pre-strip inspection. What's also important while we're doing the pre-strip inspection, visual inspection, and effectively producing a report with recommendations for rebuild is intel from the customer and the client. That's important so that we can detail our strip activities and focus in on any areas that's been causing issues, whether that have been potentially a seal leak or high vibrations or temperatures being picked up. Having that intel is important so that we can tailor our strip and really focus in on those areas. So once we've done our visual inspection, we do some extensive electrical checks, then a hydro pressure check, and then a performance check, and then ultimately detailed component inspection, all with the aim to produce a report, an SIR report with recommendations for refurbishment. So I'm going to pass you, no, I'm not, I'm going to do this slide as well. So this is the just really an introduction slide to some more detail that David's going to go into. So when a motor arrives at a Trillium workshop, an inventory of all ancillary components returned along with the motor and pump is taken. And in some cases, and in most cases, when these submersible motors are stripped down, there can be 70, 80 components, individual components. So we undertake the following initial checks. So we've got check the rotors for freedom of rotation, record the shaft axle setting, and then a test pressure is applied as per the motor operating pressure. And then also Trillium test the insulation resistance of the motor via the cable. And during this check, we assess whether winding cross connection must be split for further evaluation. So the images on the right-hand side really just show the different brands and types of submersible motors that we have overhauled. So on the right-hand side, we've got a Flowserve submersible motor. In the middle there, we've got an Indar, and then on the left-hand side with a green cable drum, we've got an original Weir design submersible motor. So all different shapes and sizes, and hopefully throughout this webinar, we'll discuss the differences and the skills that we've got whilst carrying out these works. So I'll pass you back to David now, who's going to run through some more detailed stuff around the inspection.
Thanks, Callum. The next two slides, we're going to focus on two of the key sub-assemblies that make up the submersible motor, which are critical to us during the inspection process. So firstly, the rotor pack itself, the rotor core pack itself. A water-filled motor will suffer from erosion as it's pumping a fluid internally, and it will suffer from some level of corrosion. So on receipt, we're very keen to assess that core itself. We do this by applying some gentle cleaning techniques. The reason we are very careful on the rotor OD when we're cleaning it to check condition is the insulated bar that's running along the core in most cases has a bridge slot covering it. That bridge may only be up to 0.5 mil from the bar at design. So obviously wear and service will reduce that gap down. When we receipt the rotor and we've cleaned it, we're looking to examine the core, visually review it, and trying to make assessment on the brazed ends also. One of the key dimensions we'll take, and we'll talk about this in the strip and the reassembly process, is the air gap. The air gap's measured on the OD of the rotor and the ID of the stator. When we measure this, helps us understand the wear condition of the rotor, whether this is worn equally along the core pack itself. This can usually be seen visually as the bars themselves start to become visible. Some of the key areas that we're going to look at when we're inspecting these are the brazed ends. This is what supplies the continuity to the rotor bars and core pack itself. And what we're keen to do is avoid any breaks in that circuit. Any breaks in the circuit itself could drastically impact the performance of the rotor in operation when it's been tested. This would also be shown up. What we're looking out for here is the length of time in service. This helps us determine the age of the plates themselves and how much wear we would expect to see for the length of service we've had. Also, the number of physical running hours that it's had in that time of service. This helps us determine a little bit more about the failure mode and the reason for overhaul. So on the right-hand side, this is a snippet from our standard operating procedure, which our engineers have during the repair process. So this gives an indication to the engineers what we are looking for. This is backed up with technical engineers who also review the product prior to any strip and spec report being issued. So on the left-hand side, we've got a couple of rotors that are deemed acceptable, which shows general wear, no visible slot bridges. On the bottom rotor, the general wear, there are some outlines of the bars, but 95% of the bar is covered and we see no break there. On the right-hand side, we've got two examples of unacceptable rotors. The top rotor has pitting and corrosion, so some holes starting to form in the rotor core itself, which could start to affect and delaminate the core. The unacceptable rotor on the bottom is where we can see the spines of the bars visually running all the way along, which would indicate that that bridge has worn in service and the air gap will be inconsistent on the rotor itself. Now we're going to go on to talk a little bit about the stator core. If you go on the next slide, please, Callum. So on the stator, this is similar in a process to the rotor core itself, which will require a visual examination. So as Cal mentioned in his slide, on receipt, the motor is subjected to a Megger test to check if the electrical circuit is down to earth. If this does proceed to be down to earth, we would suggest at that point to the end user that the cable is cut. This would free the cable from the windings and allow us to accurately assess the winding pack itself and the stator core. In most cases, there is some debris. As the rotors have worn in service, the stator will be covered in some dust and rust. What we would do to ensure that we have a clean stator to fully assess, to ensure we don't miss any holes in the core, is we would typically tend to leave the stator submerged for a period of 24 hours. Depending on condition, we may be able to assess quite quickly that the core is scrap and that this check is null and void. We start by visually examining the windings after they've been submerged, all the connections and bracing to see if anything's come loose. We'll then proceed to carry out multiple electrical checks to the circuit itself, firstly measuring the IR on the windings to earth. Again, if this indicates a winding fault, i.e. down to earth, we would suggest that the star point is split so we can get to each group of the windings. At this point, we will check them phase by phase. However, we don't recommend that a partial rewind is done. This just helps us understand where the fault has occurred in the stator itself. We do expect that the stator core pack would have less signs of corrosion and erosion as it's a stationary component, and we're just looking to understand the wear gap, the critical air gap going along between the rotor and stator to see if this is worn after time in service. There is examples, as I've discussed and mentioned, that we may have a high electrical reading but a poor stator core. If the core has started to delaminate, showing corrosion or erosion and holes appearing in the core itself, this would necessitate that a rewind would have to be done, as the core pack would need to be replaced. If you can go on to the next slide, please, Cal.
David. All right, so just touching now a wee bit on the sort of more traditional mechanical aspect of the submersible motor. So you can see on the right-hand side there, we've got the thrust collar arrangement. So on the bottom right-hand image there, you've got the image on the right-hand side is stainless steel coated, and then they're lapped to light bands on the right-hand side. But with different motors and different OEMs, there's different designs. Well, that be traditionally white metal coated, which we traditionally see in the pumps. And you can also see you've got the bearings there of all different modes of manufacture and materials. So on receipt at Trillium, we examine for corrosion damage and any additional wear to mating faces and spigots or registers. And we also examine for cracks, especially at the pump suction end. That's when if we see anything visually, we could then look to do any NDT inspection, whether that be dye penetrant inspection, mag particle inspection, to hone in on any surface defects that we can't see by eye and see what the level of crack or defect is. So in terms of sub-assembly inspection, as submersible motors are run vertically, inspection of the bottom thrust bearing is crucial, and we examine the thrust for scoring and damage to the keyways. So as you can see on the bottom right-hand side, it's a thrust disc with a thrust pad with sort of a rocker plate. So inspecting that thrust pad rocker arrangement and the thrust ball for any damage, especially flat spots, is critical. And typically the thrust bearings, when they come in for a service, are refurbished, either replaced with new or overhauled and effectively made back within acceptable levels for service. So I'm going to move on to the next slide now. So that's us now detailed the strip inspect report process, and now what we're going to touch on is the rebuild before we then move on to the test. So as you can see here, we'll run through a lot of these in the next few slides. We've got the stator recore, got quite a good image on that, the rotor recore and balancing operations that we do. Then moving on to the stator recore, the thrust and journal bearing refurbishment, then connection of the cable, any pre-assembly checks, and then ultimately final motor assembly before it getting loaded for performance test, whether that be no load and then load test with the pump end attached. So I'll pass you back to David for this slide.
So here in Alloa, we do pride ourselves on having quite an extensive array of skills to support the repair process, overhaul process and inspection of these motors. So we do hold expertise on the mechanical, electrical and the testing aspects. We'll first touch on the mechanical and machining. So after a repair scope is agreed with a client, we do like to undertake as much as possible in-house. We estimate this to be somewhere around about 95% of any work scope we will carry out in-house. The parts we do look to sub would be around the mechanical seals being refurbished by an OEM and the thrust pads, which are usually subbed to another support partner. Everything else is kept in-house during the mechanical and machining part of it. So this is the full machining of any replacement components, which is supported through a reverse engineering process, which allows us to tackle almost any OEM brand. We also have quite an extensive array of large machining capabilities in Alloa. This is backed up by the balance, which allows us to fully run the rotors up to full speed prior to going in. We also have the ability to machine brand new stator tubes. So dependent on the age of the unit and condition of the inner tubes that house the core packs, we have a boring mill capable of striking the full stator core landing in one continuous cut. This is crucial when it comes to the rebuild process, as any misalignment between plates could have an impact on the winding, the number of turns that can be put down a slot, or general build problems. This machining operation also supports us to remove flanges to allow tubes to be salvaged. The submersible motor is designed in most cases in a method that allows for the easy overhaul of major components. So we'll look to reuse things like the stator tube, which houses the core pack, the shaft itself. These are machined down and then fully built by hand to recore them prior to rewinding and build and test. Next slide, please, Callum.
Thanks, David. All right, so just going to run through these next couple of slides again, really just showing some more images. The first two of the rotor assembly. So as you can see there on the left-hand side, you've got the rotor assembly being stacked and then the plates being compressed. So as you'll see in the images, we do have a lot of jigs and fixtures within the Alloa Service Centre, which are crucial to make sure the alignment of these plates when they go on, and then ultimately the copper bars that run through them are all aligned. So coupled with the experience that we've got, the bespoke tooling is critical for these operations. And then you can see on the right hand side just a closer up image of the rotor pack, and then the SC rings and the bars through them. So I'll move on now and we'll show you some further images of the stator assembly. So what we've tried to show here is just the different aspects of the stator. So we've got the stator having been recored, and then we move on to the electrical stator windings. So as you can see there, we've got the arrow, because it's very much a case of we'll do so much winding, we'll then do electrical checks, back to winding. The last thing we want to do is fully wind the motor to then find a flaw in the cable or a flaw with some of the work that's been done. So continual testing throughout that process is crucial. And that tank that you can see there is very close to the clean room where the guys and girls do the winding operations, so that to obviously reduce downtime and as lean as possible. And then the image on the right hand side, we've got the full stator refurbished again on rollers to aid and a working height for when we do the winding by hand. So what I'll do now is I'll pass you back to David, who's going to run through another couple of slides.
So as could be seen in the images in the previous slides, the complexity of building some of these core packs is fairly intense, and we must ensure that this process is followed rigorously to ensure that when it goes on test, we're going to get results that are acceptable to what we believe to be design. So during the reassembly of the rotor and stator cores, we undertake several measurements and press laminations in place. This is supported as in the strip and spec process, we take several measurements again. We also map the windings, so we have all the existing data there when it comes to rebuilding. During this process, it is critical that the right materials are selected. This would be key on electrical lamination steel. Incorrect lamination selections could lead to quite a detrimental effect in operation or prevent the motor from operating at all. During the process of core building, this is all done by hand. These laminations typically tend to be around about 0.5 millimetre thick. As the photo on the top left shows you, these rotor cores themselves can be reasonably long, which could be up to 3,000 plates being applied by hand, pressed at different intervals to ensure that there's no gaps there. Gaps between the plates could lead to some heating issues on the rotor core itself, which we must try and avoid. As with the core building, all the winding process is done by hand. This is done by skilled engineers in-house, as Callum touched on in the last slide. This process is very much a stop-start process and can take up to 2 weeks in some cases. The reason for this being is that by the time a motor is fully wound, it can go through up to 12 electrical checks, which is winding checks carried out at each phase that goes in. This prevents us from fully winding a motor and cabling it before finding an issue to fault. We must try and eliminate any issue being past the test, as this will just require a full rewind again. During the winding process and prior to starting, we have the ability in Alloa with a transformer purposely built and installed to support this work that allows us to proof test the windings up to 19,000 volts. This voltage is obviously applied depending on the rating of the motor, but allows us to proof test the wire even before we commence the winding operation. Once we have wound the motor itself, we do move on to cabling. The cabling process, depending on the brand of motor and the voltage of motor being done, this can be a rudimentary tape joint, which insulates the power cable and windings. The Trillium Flow Services technique that we employ is a vulcanized joint. This involves using specialist electrical taping materials, which are heated to create one solid joint encompassing the star point, which is the connection between the windings and the power cable. This helps to insulate and support that should any seawater ingress occur offshore, this joint will help last longer. However, these are subject to wear and tear with seawater ingress, which we'll touch on later. This whole process that we employ in Alloa is under constant review. It's been evolving over a number of years. The ability to develop this process and keep developing this process is supported by the number of different OEM motors that we have seen over the years, which allows us to pull different bits of technology and understanding to try and support the best possible product across any range of motor. We do like to ensure that after the test is done, that any quality plan is either customer driven or our own internal customer driven process follows the motor to test as well. Next slide, please, Callum. So once we have taken the motor through its assembly process, all the electrical checks have been done, the motor's been fully built, all the clearances have been checked, the motor will then be passed. In every case, a motor is subjected to a no-load test prior to coupling to any pump. We do always recommend that the motor's checked first. This will prove that the electrical circuit is good and operating before put under load conditions. At Trillium Flow Alloa, we do have 2 specifically built test tanks. One does allow for a full submerged no-load test, and one full test tank allows a pump test. We carry out all the electrical tests in line with the IEC 60034 electrical standard, and we have the capability to test pump sets in both 50 and 60 Hz up to 6.6 kV. During the no-load testing regime, we will agree with a client the extent of the work to be done. The reason I say this is dependent on the level of work that's been done to the motor itself. For example, if windings are not to be replaced and are existing, some of the work scope may be reduced. This is more likely on the high voltage testing, as this wouldn't be carried out on pre-existing windings. As a minimum, we will always carry out measurement of winding resistance. The installation resistance will always check phase rotation, have these marked, so when it's deployed offshore, the tails are correctly coloured up for jointing HV offshore. We'll run the motor no load. During the motor no load, we'll carry this out over an hour's period as a minimum. During this period, we'll be recording readings every 15 minutes. We can carry out a short circuit test or a locked rotor test. This again is supported through our generator and transformer setup in Alloa. That allows us to carry out a momentary overload on the rotor itself in a locked condition to prove the electrical circuit is operating as it should. If the motor has been fully rewound, we can subject it to a high voltage flash test on the windings itself. This is performed on several units after rewind. If the motor is 6.6 kV, this would be 14,200 volts that we'd be flashing the motor to. We do carry out, as part of the mega check, a polarization index check. However, the IEC 60034 standard does state anything over 5,000 megohms. This is not a critical requirement, but this is carried out mandatory on all the units that we do check. Next slide, please, Callum. Once the motor's got through an acceptable no-load test, we are always keen to ensure that a pump end is available. 9 times out of 10, clients do send pumps to be repaired also, although sometimes these pumps can be kept in territory or offshore if a specific need arises. The reason we want to test these with a pump is this is how it will be operated offshore in a fully coupled condition. We want to ensure that that unit is set and stable for operation. The test bed here in Alloa is bespoke built to allow us to test units to as-site conditions. In the middle here, this is a pictogram showing the setup that we have in Alloa. We have 2 loops depending on the flow rate that we're going to use, and the tank itself is 6 metres deep. The image on the right shows a pump set being installed in the tank for load test. Unfortunately, as these are submerged tests, there isn't a visual aspect to the test itself. We operate the valve remotely on top of the test rig, and we record readings over an hour's period, taking readings at each flow point. The tests are carried out in line with the ISO 9906 standard, NAPI standards, and the NFPA fire pump regulations. This is obviously duty and pump specific requirements. This will be agreed prior to any test being carried out also. Thanks, Callum.
Thanks for that, David. So I'm now just going to do one slide on our upgrade offering. So as I described earlier in the sort of life cycle model slide, we do have our engineers based at our head office in Glasgow, and also extensive knowledge in the Alloa facilities. So David's going to run through an example of what we've done to effectively upgrade a submersible motor, and it kind of ties into our advanced parts solution offering that we described as well. So I'll pass you back to David.
As Callum mentioned, the Alloa Service Centre here is also backed up by a team of remote engineers who specialise in hydraulic, mechanical design, reliability also. So where a client approaches about a repeated failure on the thrust end of a submersible motor, this unit was brought into Alloa. We analysed the unit and looked to upgrade the tilting mechanism, checked the fluid circulation for cooling and lubrication, and the thrust seating arrangement also. The thrust bearing life was significantly improved, which obviously saved the client a lot of money in downtime and repeated failures. As an example here, you can see the existing design on the left and the move to the new design on the right. The key standouts from this reverse engineering process were we managed to increase the total surface area of the thrust pads by about 32% in order to reduce the load per area. We also looked to upgrade the composite thrust disc material with a standard Trillium spec material, and we also increased the thrust hub diameter by 5%. This was done while carrying out a full FE analysis of the cage and the footpiece to ensure the strength, the stress concentration and total deflections were to an acceptable design tolerance. So this is just one example of many requests we do have from customers to try and improve integrity of units, and it's something we're keen to support on. So this is something we always look to try and support alongside any upgrades and re-rates on pump ends themselves also. Thanks, Callum.
Thanks, David. So we're now going to move on to the operational review and condition monitoring of the submersible motor product. So So as you can see on the right hand side there, we've got some images actually in service. So deep well lift pumps, both suspended shaft driven type and electro submersible type, require to be started against zero head as the discharge column to the surface is initially emptied. And monitoring and maintenance of suspended shaft type driver is typically easier due to accessibility. So the condition monitoring of the submersibles is fairly limited. However, it is expanding with sort of vibration sensors, vibration monitors becoming more prevalent. However, traditionally, we've got motor coolant RTDs, which is important to ensure the temperature of the motor is stable, and continual monitoring that, and whether there's trip alarms set by the client, etc., is important that's maintained and monitored throughout the operation of the motor. The header tank level, so David will touch a wee bit in the next few slides around the header tank. Not every motor has them, but ensuring that level doesn't drop, and if it does drop, monitoring it over a level period of time is critical. And then also the sort of general process information that you get, whether that be power and current, and then reviewing that against the original test data from when the motor was overhauled. So corrective maintenance intervention involves typically removal of the complete pump string and usually return of the set for repair. But if we can do that early enough, the downtime of the submersible will typically be a lot shorter by not having to potentially do as many components as if it was let run for a period of time under duress. It can cause some significant downtime due to lead time of components and the repair time required. So I'll pass you back to David to run through this slide.
So in operation, as we've discussed, we're focusing on the water-filled motors today. When the motors are filled with water, as I touched on earlier, we would see some level of corrosion happening as the core plates themselves are made from steel. So what we recommend is that a suitable glycol mix is put inside motors. This helps to lubricate and cool the inside of the motor and also protects from freezing conditions in certain environments. We understand some clients do have these motors in hot water situations, but the glycol itself acts as a rust inhibitor to help try and protect the cores for as long as possible. We feel this is a critical part of the process, and one of the things that can be easily mixed up in the installation process is to mix the wrong material in there or put in any type of material. We do have clients approaching us asking us if glycol can be inserted of any brand. This would obviously be reviewed case by case, but in most cases, the brands that we do see are not acceptable to be used for this type of product. As I mentioned, during operation, the water is circulated within and around the windings, providing lubrication on the bearings also. The key part of the monitoring that we try to recommend, and we have looked to retrofit in most repairs that we do nowadays, is where possible, we would like to see an RTD fitted. Some units, brand new, will have these RTDs as standard. Older design units may not have these in place, and as a recommendation that where possible these are installed. There obviously needs to be an ability to connect this top side as well. But the reason we want the RTD fitted is we want this as close as possible to the motor windings themselves, as we must protect the motor insulation. In most cases, the winding insulation used on submersible motors would be rated to a maximum of 90 degrees. And this is the key thing that we're looking out to try and protect, that we don't run past that. Running the motor hotter could break the insulation down quicker, but it could also lead to a more catastrophic failure. The internal cooling methods within motors do differ manufacturer to manufacturer. Some cooling processes involve purely the centrifugal force of the thrust itself, using the thrust disc spinning the water across the face and back up through the rotor air gap and then back down pockets within the motor to circulate the water. Some manufacturers do deploy a small circulating impeller that's down at the bottom of the thrust, which also supports increased cooling flow. This is an industry standard as well, and both are of equal design and work suitably well. Next slide, please, Callum.
Thanks, David. So what we're going to move now on to is failure modes and what to look out for. So I'll move on to the next slide. So as a submersible motor specialist, Trillium Flow Technologies engage with clients worldwide to support in offshore monitoring queries and full root cause analyses. So it's worth mentioning with the submersible product that it really does travel from around the world, whether that be Angola, Malaysia. It's really the idiosyncrasies and the the technical capability to do them does effectively makes them travel, and we see them from these different countries around the world back in Alloa, really because of the capabilities and the unique skills required, and also the testing capabilities is limited as to where they can be done, and because obviously they're such crucial pieces of equipment, ensuring that they go in and operate correct first time is absolutely vital. So understanding the fault mechanism, if they're in for a routine maintenance or if there's been an issue in operation, understanding that and really getting to the bottom of that in terms of a failure mode effect analysis or a root cause analysis is absolutely vital, so that we can look at that in the strip inspect report, build in any improvements in the overhaul, and then ultimately verify that with our testing. So just briefly touching on this slide, the most common submersible fault indications are an air fault, a high motor current, a stalled current, which typically indicates a seized units, and also underperformance. So when we're doing the full root cause analysis, it can be hard to pinpoint on some occasions due to the extensive damage that we do see with the submersible motors. However, the experience, a bit of information from the client and the customer goes a long way in assisting our engineers and ultimately diagnosing the problem. So I'll pass you back to David.
As Callum touched on in his slide, there is obviously some fairly common faults that we see. So I'll just direct you to the pictogram that's on the screen. These are all examples of faults that we have found on a motor or motors returned to Alloa during inspections, showing the state, if these units are left in unmonitored and uncontrolled, how badly the damage can occur. So a little bit of what can cause this and what you may see is, for a thrust bearing damage or wear, we generally see this when we've done in-depth RCA reviews and root cause analysis to be low flow conditions, running the pump well off its best efficiency point, and duty flow. We always try to work with clients to come up with new operating regimes that may help avoid that. Some clients obviously in situ have overboard dump valves that allow us to try and get the motor or pump set back up close to the duty point, which would help support less load on the thrust itself. This is something we do fairly regularly. The winding fault and core damage, this typically tends to be an age-based symptom, and it could be exacerbated by things like motor overheating, poor cooling, poor mix of fluids on the inside as well. The mechanical seal, so we do see a loss of header tank fluid being unmonitored during this time when the header tank goes dry or is not topped up. Seawater can ingress in the motor. This affects not only the mechanical seal, as it is clearly damaged at this point, as the rotor core and the stator core can be subjected to salt water, which is obviously going to cause the iron steel plates issues and start to wear. We do see some core damage due to poor filling, so wrong material being used, wrong glycol mix being used, or completely the wrong fluid installed in the first place. We can see during installation as well, as the picture on the top right, some cable damage being caused by the cables being dragged or not properly secured when banded to the risers being installed offshore. It's important that these are monitored on the installation. We can find that header tank loss can occur if header tank hoses themselves have been damaged at the fitting points, or the hoses themselves have become burst on the installation. Whilst this is not a major issue for the unit, it can be fixed. It's an issue to pull the unit and recover this, so it's care and attention. We have a strong field service team that not only supports the pump side of the business, but also supports the motor side and submersible side of the business in following these and installing these worldwide. Next slide, please, Callum.
Thanks, David. So moving on to the next slide, really just a summary of what we've discussed in terms of the preventative measures that can be taken. So as a minimum, it should be possible to set up trending of pressure topside and motor current. And as I described earlier, relating that to what was seen from a test once it was overhauled, and trending that to see how it's effectively potentially losing performance over a number of years is important as a indicator to start thinking about early intervention from a service aspect. RTT temperature instrumentation can be retrofitted to most motors that don't have it, to add an additional monitoring point in service. Flow metering, if not permanently installed, can also be achieved using portable ultrasonic meters. Just again adds to the picture. And as we've described, the header tank level should be able to be monitored at deck, noting any losses in a 24-hour period, and setting up a regime for that to ensure that's monitored is crucial, and feeding that back to the overhaul service provider is important, so that we can start to advise of anything that may be up with the submersible motor. So that brings us to an end of the main slide pack. But what we're going to do now is just do 3 slides on sort of conclusions and a recap of what we've ran through today. So I'll pass you back to David to do this slide.
Over the next few slides, we're going to try and recap during the overhaul, during the testing, and during the condition monitoring phase for the redeployment of the unit. So to us at Trillium, it is very important that due to the complexity of these submersible product, the motor specifically, due to the variance brand to brand, that these are sent to approved workshops with skilled technicians undertaking the electrical and testing work scope. A misstep in the overhaul process can have serious consequences offshore. Not testing a unit, for example, and having the cost and burden of installing a unit and then withdrawing a unit very quickly can be time consuming and have a lot of downtime in between repairs. It's important that this is done because this will help reduce the risk of premature failures. If we know the motor has been fully tested and inspected in accordance with a rigorous QA process, and then fully no load tested and hopefully load tested if a pump is available, this will help prove the unit prior to being installed. We want to try and avoid any unsanctioned materials being used in any of these processes. Incorrectly graded laminations, as I've touched on previously, correctly specified copper bars for the rotor bars that are to be used, the correct materials used for bracing the windings in position so those don't become loose in service and move against the core plates themselves. The core pack itself being insulated with a lining paper prior to winding. These are all very important steps that we follow in-house, and we would recommend that a client does their due diligence prior to sending a unit to any repair shop. During the repair, it is critical that the electrical cores are fully evaluated. We have seen cases where some workshops, due to the complexity of the electrical work scope, have decided not to recore or rewind motors to try and avoid this. Installation will deteriorate with age. It's very important that windings are fully assessed and that we understand how long that winding has been in the motor prior to it being redeployed. This is one of the most common faults we'll see, as we've touched on, is an earth fault, which is a deterioration of that wire and the water ingressing to the wire causing the earth fault. It's also very key that the brazed areas in the rotors are fully reviewed to ensure the continuity is in place and that the air gap is of a sufficient size prior to moving on to test. Next slide, Callum, please.
Thanks, David. So just a kind of conclusions and recap around testing. So as I described earlier, it's absolutely crucial that when these motors and pump assemblies go in, that they work they're right first time. As we described, they come from across the world, and we want to absolutely make sure that our SIR and overhaul process has been correct, and that's why we do the rigorous testing that we do. So carrying out the no load test on the motor, and then the load test with the pump end attached is what we do as standard. So due to the installation and removal process and cost, as we described, we thoroughly suggest, and we do it as a standard, that we carry out a test both no load conditions and load conditions. So it's worth also noting that Trillium, we also store units for some of our clients. So we'll store them in the vertical orientation, with the idea of effectively being able to deploy one of these motors and pump assemblies at pretty short notice. What we'll do is, if they've been in storage for more than a year, we'll carry out some testing before they go, just to make sure that nothing's changed and they're still operating to the same parameters that they did prior to us putting them into storage. So I'll pass you back to David for the last slide.
Thanks, Callum. So we've talked through the overhaul process, we've talked through the testing. The money's been spent to repair the unit fully, and we want to ensure it stays in operation for as long as possible. Or should the worst happen, that a fault occurs, that it is monitored correctly, and we try and prevent any major escalation. So Trillium, we do recommend that the unit is monitored where possible. Process information gives us the best chance of diagnosing a unit which is offshore and deployed. We have reliability engineers that help us assess this and review this, where we can try and make some calculated judgments on keeping the unit running or making an agreement to remove the unit. Where possible, we want to see alarm and trip settings utilised. This can be for data such as temperature or overload current. So if an RTD is fitted and operational, this is one key indicator that can be used to try and protect the unit. We can advise on alarm and trip settings in most cases, and clients have approached us to support with this. Overload current time relays are also very important to try and protect the motor from causing a major electrical fault. If the unit is installed with header tanks, because as we've touched on, some units do not have header tanks as standard design, it is important that where a header tank is installed, that it must be monitored for losses. We recommend that this is done through a 24-hour period. If the unit starts to lose fluid, this should be topped up with an equivalent fluid, as is required to prevent any seawater ingress. If the leak gets worse, it is suggested, where possible, that the unit is pulled to remove as quickly as possible to try and prevent any major seawater ingress. If the losses do keep occurring and it is a necessity to keep running the unit can be run providing the header tank is fully topped up with a suitable fluid. Where possible, we do want to see the pump run as close to duty point. This will help improve the operating condition for the motor. And Trillium do expect, and we try to stick by this, that where the unit has been fully overhauled and tested, that it should last between 3 and 5 years before a required intervention. We do have many examples where this is much longer, up to 10 or 11 years in some cases. Our statement with 3 to 5 years is a recommended withdrawal for a mechanical review. At this point, we hope that electrical circuit and core plates are in good condition, that a minor repair is required. If the unit has been monitored correctly, ran correctly, the likelihood of a shorter repair is much better. We do believe that a good planned maintenance regime backed up with routine condition monitoring will help prevent failure by early intervention. Part of this process we are now recommending to clients is that they hold long lead spares. The marketplace has been very difficult to obtain some of the crucial spares to overhaul the motor, more specifically the winding wire in recent years. We do stock a lot of materials for customers where they're looking for this to be done. This allows us to shorten the lead times on motors drastically, and it's worth a consideration prior to removing any unit and sending it back to Scotland. Thanks, Callum.
Excellent, thanks, David. So what we'll do now is we'll move on to a couple of questions that we've got in. So if you do have any other questions, please put them in the question and answer box, or if you do have anything that you would you'd like to ask, please reach out to myself and David at another time, and we'll do our best to ask that question. So I'm going to lean on the expert again, David, yourself, unfortunately. Speaking. So I've got a couple of questions here, and the first one is, what is the most common fault you find on strip inspection of submersible motors?
So I probably tend to say that's an air fault. That's probably the predominant reason for units being pulled. We understand that cash is king and that units operating is critical for people offshore, so there is a resistance to pull units. So yeah, typically the units are pulled due to an air fault, the motor not starting. When it comes in, we can usually assess this quite quickly during the mega test, and then potentially stripping the cable off and checking directly onto the stator as well. Over recent years, we've done a bit more work looking at mechanical seal failures as well. We're aware of some units in some locations having more of an issue with transient upthrust, which causes seal faces to hang up, causing seawater ingress as well. So yeah, those are probably the two main ones that stick to mind.
Okay, thanks for that, David. And then one last question around the header tanks that we've discussed. So if a header tank is installed, does this provide cooling flow to the motor?
So the header tank itself, and I think we've potentially been asked this in another session as well. The header tank itself doesn't actually provide cooling flow. The header tank is there as a telltale sign for the mechanical seal. It provides a vent line back up to the header tank to allow air to vent. It provides cooling water from the header tank itself, fed down to the motor via gravity should the mechanical seal go. So if the seal fails, the gravity-fed system feeds the water down, and this pushes the seawater back out, but it doesn't provide a cooling flow itself in operation.
Right, thanks for that, David. Okay, Doc. Well, that brings the webinar to a conclusion. So thanks a lot to David for his extensive technical knowledge. It was really good. This webinar will be available on the Trillium YouTube channel in a few days. And as I described, if there is any other questions, please reach out to myself or David, and we'll do our best to answer any questions. So thanks everyone, and see you soon.
Thanks everyone.